It's my pleasure to make this presentation. And the title is Stability and Stabilization of Fractional Order Control System. I mainly do the work about the control of fractional order system. And outline. This presentation mainly includes three parts. First is what we have done in the previous days. And second is what we want to achieve next weeks or months. And
maybe years.
The third part is the conclusion, summarize the previous two parts. And first, what we have done. And in this part, first for normal fractional order system, here alpha is the order, xt is the state, ut is the control input, yt is the measured output, a, b, c, and unknown real constant matrices. For this normal fractional order system, we designed the fractional order output feedback controller. Here alpha is the order. This is the controller state. AK, BK, CK are matrices to be determined. For this system, we designed the output feedback controller, and this is the simulation. This is the state response of alpha in this space, in this domain. And this is the state response of alpha in this domain. From the two page, we can see that the proposed output feedback controller can stabilize the system wide.
That's a big jump even to me. Okay, we don't know what is your ABC yet, so you did simulation.
ABC is given.
It's given, okay. It's not shown, okay. But just to illustrate, then the job is doable, okay? Alright, so giving ABC is known. You measure Y, but you cannot measure X. So you need to observe X through this way, observer, output observer, and observer-based feedback control. Okay, so the job is doable.
Second, for fuzzy fractional order system, here xt is the membership function of xt. Alpha is the order, and in this new idea is the grade of membership of xdt in new idea. Then we can obtain all this. This system we call it the fuzzy fractional order system. And for this system, if we want to do the control for this system directly, it is very difficult. So we changed the system to the following uncertain parameter system. Then design the output feedback controller for this uncertain parameter fractional order system like this. And use this controller to the original system, this fuzzy fractional order system. And we do the simulation. Result is...
Can you go back a slide and add a remark? It's a big jump to those of you who never did this fuzzy dynamic system. Go back a slide. So, go back. Oh yeah. See, here you can see there's R subsystems. Okay, they are added together with a weight of h of I. And while h of I is a weighted sum. This weighted sum is based on the omega sub I. Omega sub I is called membership function. Okay? The product of them. Okay? Yeah. So to me, it's like you don't know what's the system, but linguistically you can describe in a rough way. So they could be like this, it could be like this, and this condition, and so on and so forth. Excuse me. Finally, you can quantify them, and by using this, introducing the membership function, then you can fuse them together as a fuzzy dynamic system. So that's the key essence of the fuzzy.
As a membership function, if you take space and you put it into grids, and you have a trajectory, and you have ij are the coordinates of one grid point. If the trajectory falls in that ij grid, then that gets a membership function value of unity. If it doesn't, it gets a membership function value of 0.
It is continuously defined depending on the value. So here the grade of membership function is nu ij, and the nu ij. Can you go back a slide to see where's the nu ij? The nu ij and product of this.
Yeah, that's what I mean. You have this trajectory x and j
Trajectory,
of t
yes.
is going through the system. If
Right.
it goes through the cell ij,
Uh-huh.
then the membership function is 1.
Yeah, this detailed form of this mu is not defined here. Could be defined in this crystal way, either 0 or 1, or there's a transit between the 1
Yeah.
and 0. So, yeah, you're right. So this is one of the
Okay.
choices of the membership, shape of the membership function.
Okay.
And the weight as 1, okay? Go ahead. Yeah, you don't assume everybody is an expert like you know.
And this is the simulation result. And the state response of alpha in this domain and the
Looks like it's working,
other.
but with steady state error. I don't think this is perfectly done. Okay. I'll
This
check
is
on
for
that.
that.
Well, the other
No,
peak
no, no.
was minus 120, so it's down a factor of 6.
Okay. Another previous one? This one, and the next one. Okay. This is basically again saying that observer-based control for those fuzzy uncertain systems is still working. Okay. Even if to convert the original this fused fuzzy dynamic system into an LTI linear time invariant system plus a delta uncertainty part. Even with that, it can work. Okay?
Third is for the singular fractional order system. Here, alpha is order, xtut is the definition like the previous. And here E is singular. We assume that rank E is equal to R less than N, AB are known matrices. And for this system, we give the stability condition such that the system is regular and stable. And also design the state feedback controller like this, such that the closed loop system is stable. Next is the simulation result. I think this is good.
Alright, I don't think this is right to present throughout this result to force us to believe you are right. So okay, it's fine. Next time I will tell you how to best present it. Doesn't matter, okay, go ahead.
These are in this domain.
So remember, even the E is not invertible. Can you go back 3 slides? Okay, even the E matrix is not invertible. So this system is degenerative. It's singular. It's called generalized.